Welcome to video 5.2, Hess's Law. First of all, in terms of accessing prior knowledge, a few things to consider. Remembering a little bit about the idea of conservation of energy, and that energy cannot be created or destroyed, it can only be transferred. Physicists tend to call this the first law of thermodynamics, and, little TOK sidebar. Unification of theories between sciences. How do the sciences agree? How do the sciences disagree? This will come up again in topic 5.3 where we talk about bond enthalpies. Biologists and chemists kind of disagree sometimes on how to explain energy in terms of bonds. So, something to consider. In terms of accessing your prior knowledge, you should also remember just the general idea of enthalpy change of reaction, or enthalpy of reaction, is delta H, sometimes with the little not symbol there for being under standard conditions. The big idea for 5.2, in chemical transformations, energy can either be created or destroyed. Now, I'm a little surprised actually that the essential idea doesn't include more about the idea of an energy cycle, and that's something that will come up today as well. So, understanding the enthalpy change for a reaction that is carried out in a series of steps is equal to the sum of the enthalpy changes for the individual steps. That is a key idea, and that is essentially Hess's law. And we will apply Hess's law to calculate enthalpy changes. So for some reactions, measuring delta H of reaction is actually quite difficult. Depends on the reaction. There are a variety of things that might cause that problem. And so the method we're going to use is called an energy cycle, which relies on Hess's law. And that means, for Hess's law, the enthalpy change for any reaction is independent of the route as long as the starting conditions and final conditions are the same. Reactants and products. So if I have an enthalpy diagram, doesn't matter the route, the delta H is always the same. This is an exothermic reaction as an example. We'll get some examples as we go through this, and that'll give it a bit more context. But the key is, it's only about the distance between the 2 points, sort of straight line distance if you compare it to a map. It's not about the road traveled, it's about the straight line distance. Now, looking at an example over a series of a few slides here. Apologies for not having correct subscripts here. Looking at this reaction, I've got elements in standard conditions as the reactants, and I have the products of propane and oxygen. Now, if propane and oxygen are reacted as a combustion reaction, the delta H is negative 2219 kilojoules. So that produces carbon dioxide and water. So if I want to look at the overall reaction from the elements to carbon dioxide and water, negative 2324 kilojoules per mole. And I think this particular form, reaction 1, reaction 2, and reaction 3, if we think about going from here to here, from the reactants to the products, I have path A, if you will. I have path B. If you add these two values together, they equal this value. Now let's look at it in a little bit different perspective. Let's look at it from sort of a graphical perspective. Taking the elements and reacting, if you will, to form propane and oxygen, that is delta H1. Taking the propane and the oxygen and burning them, I get carbon dioxide and water, that is delta H2. And so that means if the elements are combined in their elemental standard state form to form the products of this combustion, that would be delta H3. So this is path 1 or path 2. And so that means that delta H3 is equal to delta H1 plus delta H2. And that's what we saw on the previous slide. That's only one example. We'll see some more examples to try and make some sense of it. So here it is, just sort of as an overall, maybe a little bit better diagram. I tend to like the triangular versions as well that are not so vertical, but this gives us an idea of the relative enthalpies, and I like that. The highest enthalpies are the elements in their standard state. Things become more thermodynamically stable when we get the reactants, and even more so when we have the products. And so the products have the least amount of enthalpy and the most amount of thermodynamic stability. So they have released a lot of energy in order to be formed. So let's solve a practice problem. Let's see if we can apply Hess's law. I've got a couple reactions here. I have a reaction which is sulfur and oxygen reacting to form SO3, SO2 and oxygen forming SO3. So can we figure out from this set of reactions sulfur plus O2 makes SO2? So this third reaction would be the sum of the previous two reactions. All right, let's see what we can do. A little bit more space on this slide. So sulfur is a reactant in the overall reaction. The sum reaction is the overall reaction, and sulfur is a reactant in the first reactant. So sulfur solid plus 1.5 O2 makes SO3. That's negative 395 kilojoules per mole. O2 is a reactant in the overall, and it's a reactant in both of these reactions, so that doesn't help us very much. But SO2 is a product in the overall reaction, but SO2 is a reactant in the second reaction. So that means the second reaction, I actually need to switch. So this is reaction 1, this is reaction 2, but it's the inverse, if you will, of reaction 2. I need to flip reaction 2 and do the reverse reaction. So SO3 is going to make SO2 plus 1/2 O2. And that is negative 98 kilojoules per mole, but it is the negative of negative 98, so it's positive because I've flipped the reaction. So here's something to know about delta H of reactions. If I know the delta H of this reaction in the forward direction, the reverse reaction would have the same magnitude of delta H, but it would be the opposite sign. So if I combine these, SO3 cancels, 1/2 O2 cancels the half O2 here, and I have sulfur solid plus O2 gas makes SO2 gas. And that is negative 395 plus 98, which is negative. So, sorry, I had to pause for my calculator. My mental math is horrible. So I get negative 297 kilojoules. So this is an application of Hess's law. I'm given some reactions that I know the delta H of reaction for, and I combine them in a method that will allow me to choose a different path to get an overall reaction, and I can calculate the delta H for this overall reaction. So let's handle a checkpoint question. Take a look at this diagram. See what you can figure out. Diagram illustrates the enthalpy changes for a set of reactions. P to Q to S and P to R to S, two different paths. Which of the following statements are correct? Take a look, see what you can figure out. And the correct answer is A. So let's figure out some math. We're really trying to get from P to S, and if I go this route here, I have plus 50 minus 60, which is negative 10 kilojoules as an overall process. Here I have X, and let's use a different color. Here I have X plus 30, so X plus 30 must equal negative 10. So that means X equals negative 40. So I'm doing a little bit of algebra. So Let's see what we can figure out in terms of these statements. P to S is negative 10. Yep, got it. R to Q is positive 90. R to Q. So R to S equals positive 30. S to Q equals negative 60. Q to S is negative 60, so that means S to Q is positive 60. So I get 30 plus 60 is 90, so 2 is correct. So 1 is correct, 2 is correct. P to R. Well, we figured out P to R must be negative 40 because negative 40 plus 30 equals negative 10, and they tell us it's plus 20. Wrong answer. Therefore, the correct answer is A. So I hope that explanation was helpful for you. I kind of like this question because it's not specific reactions, but kind of gets us to think about energy cycles. Now, we got one more task to handle, and that is learning about something called enthalpy of formation, which has been hinted at in the previous set of slides. This one's pretty good. It's really useful. Enthalpy of formation is the enthalpy change when 1 mole of a substance is formed from its elements in their standard states under standard conditions. So let's look at a couple examples. Hydrogen gas plus oxygen gas are the elements in their standard states reacting to form water as a liquid. Delta H of formation for this reaction is negative 285.8 kilojoules per mole. If I take hydrogen and oxygen, I react them, and I get water as a vapor, it's negative 241.8 kilojoules per mole. Why is it different? Well, this is liquid, this is gas. Must be a difference there. Let's compare these numbers, and that's something we'll talk about a little bit in class together. Enthalpy of formation, taking elements in their standard state and forming a compound. So delta H values are usually given for standard states. That's been mentioned a few times. So the standard enthalpy changes, delta H naught, given in the literature and your data book that are measured under the following conditions. 100 kilopascals, 1 molar concentration if concentration is applicable, and substances in their standard state at that pressure, and typically 298 Kelvin. So enthalpy of formation, again, is the enthalpy change when 1 mole of a substance is formed from its elements in their standard state. So what will be the delta H of formation for elements in their standard state? 0. Elements, by definition, have a 0 value for enthalpy of formation. Not the same as saying they have 0 enthalpy, but that their enthalpy of formation is 0. Think about it. Enthalpy change is when 1 mole of a substance is formed from its elements in their standard state. So if I want to form 1 mole of hydrogen gas, I need to start with the elements in their standard state, which would be 1 mole of hydrogen gas. There's no change. Delta H equals 0. So that means delta H of formation for elements is 0. And that information will be useful for our future problems. Delta H of formation values are important. They give us a measure of the stability of a substance relative to its elements. So if it's a more negative delta H of formation, it means it is more stable. These values can be used to calculate the enthalpy changes in all reactions, either hypothetical or real, and this is a critical bullet point and something we're going to get to. Let's first start by just kind of coming up with an example of writing the equation for the delta H of formation for a compound, and in this case we're going to use ethanol. Ethanol is C2H5OH. It's not a gas. Standard state, it's probably going to be a liquid. C2H5OH as a liquid. See what we can come up with. What are the elements? Well, we need some carbon, we need some hydrogen, we need some oxygen. We need 2 carbons, and carbons is usually graphite. Sometimes we write carbon and then the word graphite here. or more commonly, we can just write solid carbon. Hydrogen gas, I need 6 hydrogens. So that means I need 3 H2s as a gas. I only need 1 oxygen atom, so 1/2 O2. And that's as a gas. And here it is written a little bit nicer for you. Sorry, I should have included a liquid. So I have written the enthalpy of formation for ethanol. I've written the equation for the enthalpy of formation of ethanol using the elements in their standard states. We're not going to use some crazy compounds that have elements we don't know about and what their standard state is. Carbon, hydrogen, oxygen, nitrogen. We're going to be using pretty simple elements that we would know about in terms of their standard state. But let's think about what this can give us. All right, if I've got reactants going to products, that is the delta H of reaction. That's the reaction we're interested in. But if I take the elements and make the reactants, or take the elements and make the products, I have 2 different sort of sets of delta H of formations. So this is path 1, and this is path 2. So that means delta H of reaction, I need my little knot there, sorry. Delta H of reaction is the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. Let's see if we can figure out where this minus sign comes from. This is, if I call this reaction 1, reaction 2, and reaction 3, this is reaction 1. So 1 equals 2. So this will be reaction 2, delta H of formation of the products, minus reaction 3. Because in order to go from reactants to products as path 1, and from reactants to products using path 2, in this path I have to reverse this reaction. So that means I have products minus the sum of the delta H of formation of the reactants, because of the way the energy cycle works. Now the cool thing is, in our data booklet we actually have delta H of formation for a number of different compounds. Very handy information. So let's use that information to calculate the enthalpy change for this reaction, the burning of propane. We're actually given some values here, although we could have gotten them probably from our data booklet. So let's see if we can handle this here. So delta H of reaction is going to be the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. So delta H of reaction is going to be 3 times CO2 plus 4 times H2O minus 1 times C3H8 propane plus 5 times O2. Products minus reactants. These values are going to come from this table, but wait, there are 4 compounds and only 3 in the table. What's happening? Let's figure it out. I think we'll be okay. So 3 times CO2, which is negative 394, plus 4 times water, which is negative 286, minus negative 105, plus 5 times 0. Remember, elements in their standard state have an enthalpy of formation of 0. Now I'm going to ask you to bring out the calculator and do a little bit of math and solve the algebra here and see what we get for an answer in kilojoules. Through the wonders of modern technology, there is your answer. I got a negative 2,221 kilojoules. Kind of significant figures wise, these 3s and 1s are whole numbers, exact numbers, so I end up getting 4 significant figures here. I only have 3 significant figures here, but I'm doing addition. They're both significant to the 1 spot, so that means I can actually keep 4 significant figures. negative 2,221 kilojoules for the combustion of propane. This is a combustion reaction. Delta H of formation of the products minus delta H of formation of the reactants. These are sort of my half steps here along the way. Now, how do we do? Negative 2221. Here's our data booklet. Propane. Negative 2219. We got negative 2221. Not bad. We'll talk later in 5.3 especially about where some differences arise. I think a difference of 2 kilojoules over the course of an answer that's over 2,000 kilojoules is actually really close. So we did a lot of learning there. Thanks for your work on that. We've got a couple more things to get through and we'll be done. Checkpoint question. Hydrogen peroxide slowly decomposes into water and oxygen. And there's your equation. Calculate the enthalpy change of this reaction from the data table. You're given the data here. This is like a paper 1 question. Check back for the answer. So, correct answer, D. Let's see how we did that. We have delta H of reaction is the sum of the delta H of formation of the products minus the sum of the delta H of formation of the reactants. The products, I have 2 times water, which is negative 286. And I'm going to skip oxygen because it's going to be equal to 0. Minus 2 times negative 188. So I'm subtracting a negative number here. So 2 times negative 286 minus 2 times negative 188 equals negative 196 kilojoules. And that is the answer, or kilojoules per mole, kind of as written. In terms of these units, it's often the case that we write either kilojoules or kilojoules per mole, even though the equation up here has 2 moles. I think of this number as sort of as written. This reaction as written would release negative 196 kilojoules, exothermic reaction. So as a summary, energy is conserved in all chemical reactions. The path of the reaction is irrelevant to total energy changes, Hess's law. And energy cycles can be used to calculate enthalpies of reaction for reactions that would be difficult to measure directly. In terms of TOK, Hess's law is an example of the application of the conservation of energy. What are the challenges and limitations of applying general principles to specific instances? Things that make you go, Nature of science. I think we'll hold off on this one in terms of a discussion for now. We can come back to it later if you'd like to. Connections to other topics. Certainly Hess's law connects to the idea of conservation of energy. We can use enthalpy cycles and we can use it to calculate the delta H of reactions. So just a look at how it can be applied. Thank you for listening. I do appreciate it. Now, questions or feedback go on the forum on Haiku, but even if you don't have questions or feedback, give me your answers to the checkpoint questions, please. Thank you very much. Have a great day. I'll see you in class.